Hey everyone, I want to make a very short video introducing you to a new statistic that we're going to be using, the F statistic. So let's share up the notes and we'll go through this. This might be a real quick one. So here's the basic idea. So what we eventually want to do is analysis of variance. That's going to be our primary use for the F statistic, but not yet. Right now, I just want to introduce what it is. So the F statistic is a statistic that we use that makes a particular kind of sampling distribution, F distribution, unsurprisingly. And so here's the idea. So the F statistic is, excuse me, I'm going to make this a little bit bigger so we can see it a little bit better. The F statistic is a ratio of sample variances. That's what it is. So if you have two normally distributed populations that have equal population variances, so sigma 1 equals sigma 2, sigma 1 squared equals sigma 2 squared, excuse me, the variances, then you take a sample from each one of those populations and you make a ratio out of the sample variances that you get. So you get this, S1 squared over S2 squared. The distribution of all the possible combinations of S1 squareds over S2 squareds gives you an F distribution. So that's what an F statistic is. It's just a ratio of sample variances from two different populations that are assumed to have the same population variance. So there are samples from each or two populations. So you get different degrees of freedom from each of the two populations. They're both n-1. So however big the sample was from your first population, it's n-1 degrees of freedom there, or n1 minus 1, I should say, degrees of freedom. Same thing for the denominator, n2 minus 1 degrees of freedom there. Very straightforward. Here's a picture of some F distributions. You can see they kind of look like when we look for chi-square distributions. However, they're different. So chi-square distributions have a mean of the number of degrees of freedom, and depending on what you're doing, the bigger your sample size or the bigger your table, depending on what kind of chi-square test you're doing, have more degrees of freedom, and so the mean goes further and further to the right as you get larger numbers of degrees of freedom. But that is not the case for the F statistic. F statistic has a mean of 1 always. Yeah, so you can see right here, all F distributions have a mean of 1, and you can see that in this picture, right? Here's, I've graphed all of these. I used Desmos, I think, to graph these guys. So maybe I should zoom in a little bit here. Can I zoom in? There it is. You'd think I'd know by now. Right, so F with three numerator and 5 denominator degrees of freedom is this kind of squared off looking guy over here. This one, where F has 50 numerator and 50 denominator degrees of freedom, is starting to look very much like a normal distribution. And in fact, if you get an infinite number of degrees of freedom in both of them, you do actually get a normal distribution. That's not a thing we're gonna need to worry about, but that is a thing that's true. So what you've got here is something that it has vaguely the same shape as a chi-square distribution, but is always centered at 1 rather than whatever the degrees of freedom is. Yeah, that's kind of all I want to say about what an F distribution is. Here is some extra credit for you on the third test. These are worth 1 point each. Do them before the test and show up with the answers ready to go on the test. So I'm not gonna like put this on the test. You just have your answers ready and like scan it in with the other pages. So using just that definition of the F statistic, which is a ratio of two sample variant or two, oh, I said S's, it's actually S squareds from populations with equal sigma squared. Sorry, my bad there. These are variances, not standard deviations for both. I want you to explain to me, 1, why the mean of all the F distributions is 1. 2, why you can never have a negative F statistic. And 3, why are they all skewed to the right? Of these, B, that I called number 2 just a second ago, is by far the easiest one. A is somewhat challenging, and C is much harder. It'll take you a while to do C. So I probably should have put these in a different order, but try B first. It's the easiest one. You can probably do A as well. C will take some thinking. And by the way, you are welcome to talk to other people about this. If you can get a good explanation from somebody else to learn it, you are welcome to describe it using your own words. You can't verbatim copy what somebody else did, but you are more than welcome to get help learning it and then explain it to me. They're worth a point each on the test, so that's 3 extra credit points that you can get there before the test even starts, right? You can sort of cheat your way to 3 points if you want. Don't cheat, right? Don't copy, but yeah, you can pre-get 3 points. There is a FCDF in your calculator, and the formula goes like this: FCDF, left, right, numerator degrees of freedom, denominator degrees of freedom. It finds the area in an F distribution, unsurprisingly, just like every other CDF, just like normal CDF or TCDF or chi-square CDF or whatever one you're using. It'll find you an area, and you just identify the F distribution like this: numerator degrees of freedom, denominator degrees of freedom. So let's do a couple of these, and then we'll end the video. I think I've still got the calculator open, right? Oh shoot, it doesn't like when I it doesn't like when I maximize my window. I can't get to my toolbar. Go grab my calculator. Oop, there we go. All right, cool. Let's share up the calculator and we'll do some of these. So just going to look in the same place as always. For my CDFs, it's in distributions. So second var is to distributions. FCDF is down here. We got FPDF and FCDF. As always, we're not going to use PDF, and we'll use CDF a bit. And then there's another way we'll find areas in F distributions using just the ANOVA command a little bit later. But for right now, FCDF, that's the thing we want. So let me flip back and see if we can find an area. We'll sketch a picture too while we're here. Yeah, so we want to find the following areas. The area to the right of F equals 2.45 on that distribution, F1723. So we're just going to graph it like always. It's going to look pretty much like you think it's going to look. This is F1723. We want to go 2.45. I totally forgot my own number. 2.45. That is in fact what I said. Okay, good. So remember, 1 is like here. So 2.45 is over here. 2.45. And the area to the right of that is this area right here. And so I am going to do FCDF 2.45 up to infinity with 17 and 23 degrees of freedom. That's it. So we're going to go FCDF 2.45 up to a lot. Degrees of freedom for the numerator is 17, denominator is 23. Paste it in. There you go. 2.3%. That's it. FCDF works just like you'd want it to. Works like the other CDFs. It's just we have to have 2 different degrees of freedom to identify which distribution we're talking about, because the shape changes depending on your sample in both the numerator and the denominator. So we got a set of 2 of them for every one of these. So let's do the last couple, and then we will call it a video, and I will go on to explain the next one. So area to the left of F equals 1 on this distribution, 5075. Now I'm going to comment on this comment in just a second, but let's find that first. So to the left of 1, FCDF was 0. All right, so we're going to go from, so the minimum value of any F distribution is 0. It only goes down to 0. And I said I wanted it to go up to 1, so 0 to 1, with 50 and 75 degrees of freedom. Paste that in. There we go. This is not exactly 50%. And so my question to you is, why? Why isn't that 50% if I said that the mean of every F distribution is 1? I'm going to pause here, and I want you to pause and think about that. All right, so pausing. All right, I hope you're back from pausing the video and thinking about it. So here's the idea. F distributions are not symmetric. They are skewed to the right, right? If you get a lot of degrees of freedom, they start to look pretty normal, but not entirely. They never really get all the way there. So if you have, so what did I say? It was like 50-75, right? So it's going to look most like this bottom one, the 50-50 one, right? So this guy right here. So the thing you want to remember is the cutoff point where there's 50% of the area to the left and 50% of the area to the right is not the mean, it's the median. And this distribution is not symmetric, so the mean and median are not equal to each other. The mean, because this is skewed to the right slightly, it's actually not all that skewed to the right, but because it is skewed to the right some, the mean gets pulled to the right where the median does not move. So that means there's a little bit more area to the left than there is to the right. So that's why the number that we got here is a little bit more than 50%, not a lot more. Now, if we had, right, so 50.7%, if we had done the same exact sort of experiment with a much smaller number of degrees of freedom, it would be a lot more, it'd be a lot more noticeable. So for instance, let's go look at, so you can see like 3.5, F3.5 is very, very skewed to the right. So let's do FCDF of from 0 to 1 with 3.5. We should get a much larger number, at least according to this picture. Let's see what that looks like. So if I do distributions, FCDF from 0 to 1 with 3 and 5 degrees of freedom, that's not nearly as much larger as I thought it would be. Sorry, I haven't done this. I haven't done it with that particular one. Only 53%, but bigger, just not as much as I was expecting. Yeah, so that you can tell that the more skewed to the right it gets, the further the mean gets pulled to the right. And so that's why it's not exactly 50%, because the mean and median are not equal. Remember, you always want to think of the 50% dividing line. That's not the mean. That's only the mean, that's only equal to the mean in symmetric distributions, which this is not. F distributions are not symmetrical. Okay. Back to one last question. Nope, not this one. Let's scroll down a bit. Area between 0.68 and 3.19 on that distribution, F418. This is the sort of distribution we're going to get a lot when we do ANOVA, something with a small number here and a big number there. So we'll explain why when we get there. So I'm just going to do FCDF 0.68 up to 3.19 with 4 and 18 degrees of freedom. So second bars, 0, say 0.68, 68 up to 9 with 4 and 18 degrees of freedom. There you go. That's how you use FCDF. We'll use that a little bit when we do a 2-sample F test, which is going to be in the next video. And then in the video after that, I will explain ANOVA, which does take some explaining. That one, ANOVA is a little complicated. 2-sample F test, on the other hand, very straightforward. So anyway, that's all I really want to say here. I'm going to go ahead and cut the video here. I will explain a 2-sample F test in the next video. And then after that, we will explain ANOVA. And that'll be it for this week. So I will see you guys in the next one.